Right. So sorry. Welcome back for. I'm so sorry because the connection is loose. The connection is lost. So let me check how to get eggs. Okay. How to get eggs in the calculator. Come on. Oh. So we need to use ln or three divided by. Oh, sorry. Ln ln 1.3 divided by ln 4.3 0.91 4 divided by 3 Okay, this looks good. All right. Okay, so now let's move on to number three. Initial rate data for the reaction are given the table. What is the rate law for the reaction? Same thing like the previous one. So now we have the constant value here, and then this is the number, right? So what we can do here is like just um, do H2, right? So okay, now let's use a rate. Okay, H2 and then Cl2. This is M, this is N. And then 2.5 divided by 1.3 is around 2, right? And then you know the H2 is same, so it should be 1. And then Cl is around 2 as well. And then N, right? N should be just 1. So Cl2 is 1. So it should be there. So we can eliminate this one. We can eliminate this one. And then let's take a look at for H2. Okay. Now, uh, 50 divided by 15. And then 10 divided by 25. And then we know this one is N, right? This is 1. And then 0.5 divided by 1.3. This is rate to get the M, right? So let's calculate that one. 50 divided by 15. So this one is 3.33. This one is 10 divided by 25. So this one is 0.4. And then this one 0.5 divided by 1.3. And then now this one divided by 0.4. So this one is only or 1 and then 3.33 m. So m is should be 0. Okay, so the correct answer will be B. It's pretty easy to get the correct answer. All right, now let's move on to number 4. The gas phase reaction proceed by biomolecular collision and and between A2 and AP2. The rate law is blah blah blah. If the concentration of both are double, the concentration of both are double, the reaction will change by factor of, okay, the reaction rate. If double, just like 2A and 2B, so it just, we know the correct answer, like I mentioned, we know if we are doubling this part, okay, we are put our double, so what happens to the rate? Let's plug in into the rate law. Okay, so the previous one is just A2 and then P2, and then if both are doubling, just A2 and then P2, so K, it will be 4 A2 and then P2, so it will be 4. Okay, it's pretty easy. Okay, now let's move on for number 6. The decomposition blah blah blah. The initial concentration is this one. This is the initial concentration. The rate constant equal 0.2. What will concentration be after 45 minutes? Okay, after 45 minutes. Now let's break down one by one. Okay, so as you can see, guys, in this case it follows the second order. Okay, the second order. Okay, and then 45 minutes we need to convert into the second, so it's around 2700 second. Okay, so now we need to use the second order integrate rate law. Okay, the second order of rate law, it will be like what? Oh, okay, I will derive the second order reaction, so to make it more clear for us. Okay, now we know from the reaction we have like 2A, and then this is product, right? Yes. So to get rate is, okay, the rate of this one, it will be what? It will be uh when like this is half, right? And then TA per TT. Okay, rate is TA per TT. This is minus because it's like decreasing the reactant. Okay, because of lost the reactant, we know that the TA per TT, it will be 2 of rate. Rate is minus K, right? And then A square. Okay, all right, A square. Okay, and we know we can proceed with the kind of like integration stuff, and then at the end we will get kind of like this way, a and then minus a0 and then plus kt. Okay, using the integration stuff. If we don't, so if we want to proceed completely, is quite difficult. Okay, it's quite difficult. I want to make it like easy, however we can do it. Okay, we can do it together. So now this is, oh, okay, we need to put in here. Okay, so this one kind of like this. Okay, so ta per tt, this is minus, we can put it over here. Okay, this is plus, right? And then using the differential rate equation, we will get like minus ta per a square, right? A square and then k t t t minus k t t t. This is, we can put in over here like this, and then this is a0 and then e final, or yeah, it's final, or e at that time, and then this one is 0 till t. This is, you can put in like a t, and then using the integration, right, we can use like dx square, we will get like uh with the integrate rate equation, we will get like at, right, minus a0 and then kt, right? Okay, so at the end, at, it will be kt plus a0. This is for the second the second order reaction. So we have couple of, I mean, we if we like dealing with this equation, we need to consider like a lot of stuff, right? So using this way, we can see, now we just plug in over here. Okay, at, because we want to know at, right? K is 0.020 liter mole second, and then T is 2700 second. We can cancel out second, and then for the initial concentration is 0.050 m. Okay, now we can see over here, up, k t, k is what? Okay, yes, that's true. So 0.05, and then so let me uh, this is 54 plus 0.05. Okay, and then in this case we want to times 0.05, so 54 times 0.05, 2.7. Oh yes, one, sorry, one divided by what, 0.05, so it will be 20. So this one is 74, 1 per AT, so AT will be 1 divided by 74, so 0.013, so the answer will be C. Okay, this is the answer of I just wanted to erase everything, guys, so because we don't have any space right now. Yeah, so yeah, please remember the equation of each uh second order rate, like integrate rate law for each order. Okay, I will writing down over here. Okay, now for the zero order. Okay, for zero order it will be AT A0 minus KT. For first order, for the first order, we will have ln AT ln A0 minus KT. Okay, for number 2, for the second order, we will have AT equal A0 plus KT. Just remember this equation, you will be fine. Okay, good. And then remember again, we have also half, right? Half reaction. So for half reaction, we can use like what? Wait. If we want to use zero reaction, put in there plus, right? And then A0 to K. And then for this one, 0.693 K. This for half-life, okay? And then this one, it will be 1 K A0. Okay, right. So now let's move on number 7. If the half-life reaction is independent of concentration, the reaction can be independent if half-life reaction independent of concentration. Okay, let's take a look at for reaction of here. It should be this one, right? Okay, it should be only the first order. So only the first order, because there is no what's that? There is no hmm, there is no concentration. Okay, there is no concentration. I mean, not dependent. Okay. Okay. Right. Number 8. The activity of radioisotope is 3,000 counts per minute at one time and 2,700 counts per minute 48 hours later. What is the half-life in hours in the radioisotope? Okay. So now we have half-life from decay. Okay. This is using first order decay formula. Okay, this is just the first decay formula. We need to determine K first. K first. We need to determine K first. How to get K? So 80 now is 80 AO minus EKT. No, not minus. Okay, kind of like this. All right. So we need to determine K. 80 is 2736. A0 is 3,000, right? The initial one. Then exponential, we know K, and then we want to know the T, 48 hours. So we put in here like per minute at one time. This is 48. It's okay. We can put in hours here. So we can use ln. Okay, we can use ln 2736 divided by 3,000. Okay, minus, right? And then so it will be, and then K, it will be 48 divided by 0.0092. So K, it will be 5 to 1.7. Okay, so now just 0.9693 divided by 5 to 1.7. The answer will be what? Okay, let me see. So This is still ln, okay? No, this is not ln, okay? 0.092 divided by 48. It should be 0.0191. Oh, sorry. 0.00191. Then 0.693 divided by n, so it should be a t half. It should be 361 hour. So this one, the answer. Okay, good. After 55 years, what mass gram? So the what mass remains of 200 gram radioisotope with half? Okay, t half is 10 years. Okay, the initial is 200 gram. Okay, so in this case we don't need to use the equation. If we want to dealing with this question, we can get the answer actually. However, if we don't use the equation, it will be quite complicated to us. Okay, so what I want to do here is just pretty simple. Okay, so we know that the total time is 55. Okay, and you know, for like 200 gram, the half time is 100, right? And then this is amount mass, right? And then this is time, so this is 0. And then after half time, right, it will be 100. And then after, this is for first, second, and then for the third one, oh, the half time is 10, right? Let me see. So it will be 10 over here. And then if we put in 20 years, it will be 50. And then if put in like 30 years, it will be 25. And then 40 years, it will be 12.5, right? If we put in 50 years, like it should be around 6 point what? 6 point what? 12 point, oh, just 6.25. Okay, so now if we put in 60, it's around 3.125. This is gram, okay, in gram. So we want to look at the value that above 3 and then below of 6. So the answer will be B. It's pretty easy. You don't need to know the equation of this one. So yeah, we could. Okay, we could. If we know the concept of half reaction. Okay, if the reaction is first order in O3, which plot will be linear? Remember, the first order, like ln, okay, remember ln AT ln A0 minus ln AT ln 0, like minus KT. Okay, so which one that will be linear? This and this. So the answer will be D. The answer will be T number 10. Yes, T. Good. And then now let's move on number 11. The experimental data from a certain reaction describe what is the most likely order for this reaction. Okay, uh, just it's pretty simple. Which one that give us the straight line? Straight line is only this one. So this is ln A. Ln A indicate that it should be the first order. Number 11 should be first order. Okay, right? And then if A kind of like this, okay, just remember this one. AT. So I just want to write it into again. 0. It should be AT is 0 minus KT, right? Okay, and then for 1, it should be ln AT ln A0 minus KT. Or of 2, it should be what? AT A0 minus KT. Oh, this one is should be plus. Okay, AT. Okay, remember A, T, and T, it will be, this one is for, if this one is straight line, it will be for 0 or order. Okay, now let's move on to number 12. Consider the reaction potential diagram. What's describe the catalyzed forward reaction pathway? Okay, EA, so energy activation is around 10 kilojoule, and then delta each reaction for forward is from here to here. Okay, is around what? This is 10, so it will be 20 on just 15. So 15 and 10 kilojoule. So the answer will be B. Okay, number 12. Oh, it looks like we are getting wrong over here. Let me double check why I'm getting wrong. Getting wrong is pretty normal as long as we learn why we are wrong. Okay? Oh, okay. So, in this case, this is the delta H, right? And this one is EA, energy activation. So, because of the delta H, like product lower, so it should be minus. And if product higher, it should be positive. So it should be A. We just getting wrong for the sign because this one is lower than in the product, right? If product are lower, which mean, okay, product are lower than the reactant, so it should be minus. This is reactant, right? Then this is the product. So see, this is minus, right? Okay. And then we have another one. In this case, the delta H should be positive. Which line segment represent the activation energy for the reaction between C and D to form A and B? Okay, as you can see, guys, now the previous one is forward. This is the backward. Okay, the backward reaction. Okay, backward reaction. We are going to backward. So CD. Okay, we need to understand line 3. Okay, this one, the activation energy. And then 2. Okay, this is for forward. This is activation energy for forward. Okay, and then for 3, for reverse. And then this one for delta H itself. Okay, activation energy for C to D to form A and B, it should be only 3. Number 13 should be D. Yes. Okay, just remember this one. This is activation energy from, because you can imagine this one is reactant and then going up and then down again. Yeah, till here. So this one, it should be activation energy for C plus D to form A plus B. Okay, why not 2? 2 is for if we want to make the reaction from A plus B to C plus D. So it's kind of like this way. Okay, so number 13 should be D. Now, number 14. A certain reaction has minus 74 activation energy. What is the activation energy of the reverse reaction in the presence of the same catalyst? So we need to now use the relationship of delta H. Okay, delta H is E in the forward minus E in the reverse, right? So now we want to know the reverse reaction. E reverse should be E for forward minus delta H. So see, the activation energy is 40 kilojoule. Okay, and catalyst is found that lowers the activation of forward reaction. All right, so we know it should be 25, right? $25. Wait. Oh, okay. The activation is the previous one is 40, and then lowering 15, so it will be 25. We wouldn't put it 25. Delta H is minus 75. So this one, it should be 100 kilojoule per mole. So the answer will be D for number 14. Yes. Just remember, delta H is E forward minus E reverse. Okay, and then E reverse, right, is E forward minus delta H, right? And then as you know, E forward, okay, E forward is activation energy. So if catalyst is found lowers the activation energy like 15, so the total of like this one is just 25, and then minus 75, it will be 100. Okay, number 15. Which statement best explain why the activation energy is changed by adding catalyst? Okay, the catalyst changes the reaction mechanism. Nope, nope. Okay, no, not change the mechanism. Okay, the catalyst change free energy reaction. Oh, change, yes, change the reaction mechanism. Yes, yes. I mean, not accept. Okay, best. Okay, so the answer will be A. They will try to find out the alternative way. Okay, so kind of like change just alternate the pathway. Catalyst change the free energy. I mean like delta G or Gibbs energy. Nope. Kinetic reaction. Nope. Okay, there is no add energy. Kinetic of reactant. No, right? The catalyst lower reaction volume. No, there is no relation between volume and increasing concentration. Nope. So the answer will be A. Number 16. Why A is correct? Because the catalyst is like providing the alternate pathway. 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 Okay, number 16. Which reaction rate is more affected by change in temperature? By changing in the temperature. You know, the reactant in the first reaction is consists of 2 moles. Okay, 2 moles. This one is just 1 mole. Okay? So now we need to know the was that the this one K will be A and then exponential like minus EA R T, or we know that this one ln K ln A minus EA per RT. Okay, EA per RT. So you know, if we are having um if we are increasing the temperature, okay, we want to know the EA, right? If EA is 1, okay, according to Arrhenius formula, if we are, I mean, if we have larger EA, it will more sensitive to temperature. Okay, if we have greater EA, it will increasing the what's that? We will increase the rate of reaction. Okay, so which one that the greater one? EA greater greater. EA more sensitive to temperature. Okay, if energy activation is larger, okay, if we have like higher EA, if we increase the temperature, okay, reaction 1 because the activation energy is lower, no. Reaction 2 because the number of molecules is increased, no. Reaction 2 because the activation energy is higher, yes. So just remember, larger EA, it will be what? Greater sensitivity to temperature. What will increase the value of rate constant for elementary step? Elementary step, which mean is 0. So rate is K, right? Oh, sorry, this is rate constant for elementary step. We want to know like this one again for elementary step is K A A R T. If the rate is constant, okay, we want to pause this one first. let's start for number 17 again. Okay, so just reminders: catalyst lowers energy activation. Okay, lowers energy activation, so K will be increase. Okay, rate will be increase. And then raising temperature will increasing K as well. Okay, and then concentration change the rate, not the rate constant. Okay, concentration change the rate, not the rate constant. So what will increase the value of rate constant? Increase the rate constant K. Okay, only K. What we want to do is which one that increase K. Adding catalyst, it will what? It will increases K. Okay, it will increases K if we are adding the catalyst. Number 17. Okay, adding catalyst. Okay, it will lowers EA. Okay, catalyst lowers energy activation. Okay, both catalyst and temperature affect K. Okay, it also K. Increasing the concentration product, nope. Increasing the concentration, nope. There is no relation. However, the most and direct and universal factor is only one. What it is? T, which is temperature. To increase the K. Okay. The Arrhenius equation describes the relationship between the rate constant K and energy of the activation. In this equation, A is empirical constant, R is ideal gas constant, E is the base of natural logarithm or exponential, and T is the absolute temperature. According to the Arrhenius, at constant temperature, reaction will lower activation energy. Reaction with lower activation energy more rapidly. So we want to know, like, if E is -1 and then E is -2, what's the number? If E is -1, if E is -1 is error. Okay, or maybe if E is -2 and then this one is -3. If E is -2 and then it will be getting error again. So if E is -3, still error, right? So just like 4, or maybe, so it's just 1 and 2. Okay, if E is 1, like 1, it will be 2.71, and then if E is 2, it will be, say, 7. Okay, so what we want to do here is we need to increase the value of this part. Okay, so now let's take a look at the option. At the constant temperature, reaction with lower activation, so which mean If we have EE like 4 and then EE with 2, so 2 will, if the temperature is like maybe still 4, this one is 4, so the value of this part will be lower. So we can say uh the the process will be the process will be more rapid. Okay, the process will be more rapid. Yeah, right. Because remember, this one is having minus. Okay, because this one is having minus. So this is 1, this is 0.5. And remember, smaller EA, smaller energy activation, will affect kind of like larger K and then faster reaction. Okay, if we have like smaller energy activation, okay, it will, so because the first part is, I mean, if you are looking at the diagram, so if we have like lower EA, the reaction will be faster, right? The reaction will be faster rather than if we are having kind of like this. It will be takes time to achieve this part. Okay, it will takes time. So the reaction will be faster, which mean the rate constant will be also larger. So at constant temperature, reaction with lower activation energy, lower EA, will be more rapid. Okay, this one is looks correct. But take a look at for others. At constant temperature, reaction with lower, this is wrong. Okay, like I mentioned before. If the reaction has lower EA, which mean has lower energy activation, it will give like much more rapid for the reaction. Okay, and then number for the option C, at constant energy of activation, if the energy activation is constant, reaction at lower temperature proceed more rapidly. Proceed more rapidly. At lower temperature. If we are lowering temperature, which mean if might be like 4 becoming 2, this is still 4 for example, so the minus will be bigger. The minus will be bigger. Okay, which mean if the minus will be bigger, we will have like slower reaction. Just remember, like at lower temperature, the reaction will be slower, right? Okay. If energy activation is constant, reaction with smaller value of A proceed more rapidly. A is constant, okay? Doesn't affect speed, okay? Doesn't affect speed unless changed by catalyst, which is not mentioned here. So the correct answer will be A. What will be the effect of increasing temperature of reactant that are known to undergo an endothermic reaction? Okay, endothermic reaction. And then we have the exothermic reaction. Okay, so we need to know what's the meaning of we remember exo kind of like absorb, right? uh yes, right, we need to know what's the meaning of endothermic reaction. So exo like, okay, if the effect okay, so increasing of the temperature undergo the endothermic reaction. Hmm. Okay, endo is absorb heat, right? Endo is absorb heat. Exo is oh yes, exhale. Okay, exo is release heat. Okay, release heat. It needs energy to proceed. Okay, think of like we are cooking food. Okay, you will add heat for the reaction to make it happen. Okay, so in this case we will have heat plus reactant and then product. Belajar. What will be the effect increasing the temperature of reactant that are known to undergo endothermic? So, endothermic, adding heat to make the reaction happen. So the rate of reaction increase, and the value of the equilibrium constant decrease. The rate of reaction, if we increasing the temperature, so the rate of reaction will increase, okay, not decrease. Okay, so if we increase temperature and heat is a reactant, so the system towards the product to get rid of the extra heat. Okay, so the rate of reaction will be faster. Okay, so we can eliminate this, and then the value of equilibrium constant is unchanged. This is not correct. Okay, put the rate of reaction and the value of equilibrium constant increases. Number 19. Oh, not this one. So I just not to want to know. Okay, the principle of Le Chatelier principle is if we increase the temperature and heat is a reactant, the system shift toward the product. That means we will get more product. Okay, so if undergo in endothermic, okay, we will have the reaction towards shift towards the product, because actually like we have heat over here and we adding heat, the reaction will shift to product. Okay, we will get the more product form. And then how about the equilibrium constant? Constant. As you know that if we have if we increasing the, so equilibrium constant is K product divided by reactant, right? And then we know it will increasing K. So put off the rate of reaction and the value of equilibrium constant increases. Yes, the A of, okay, the answer will be A. The value of equilibrium constant. Higher reaction rate. Okay, so favoring product formation. All right. So, okay, number 20. The change temperature from 10 to 20 is found to double rate of particular chemical reaction. How did the change temperature affect the reaction? So, if we increase the temperature, and then in this case, double rate of particular reaction, how did the change in temperature affect the reaction? The number of molecules with sufficient energy to react increase. The number of molecule with the activation energy increase. Double rate. Number of molecule with sufficient energy to react decrease. Double rate. Okay, double rate. Okay, the number molecule will increase, right? If we double, if we increase the temperature. Okay, right. And then number 21, the value for rate constant of reaction can generally be expected to the value of rate constant K. The value for rate constant can generally be expected to decrease with increasing temperature. The value, so K will be larger if we increasing temperature. Increase, yeah, this one I think B. Decrease with the increasing temperature only when the reaction is exothermic. So exothermic exothermic heat in the product, and endothermic heat is reactant. So if we increasing heat, there is no correlation over here. So the K the K will decrease with increasing temperature only. So exothermic heat in the product. Not K, I think it should be equilibrium constant, not K, not the rate constant reaction. K and K capital is different. Okay, so the correct answer should be B, I think, number 21, B. Yes, good. The reaction with different activation energy have the same rate at room temperature. The reaction with different EA have the same rate. K1, K2 is same. Which statement correctly describe the rates of this reaction at the same higher temperature? At the same higher temperature. The reaction with large which statement correctly describe the rates of these two reactions at the same higher temperature? The reaction will with the larger activation will be faster. The reaction with smaller activation energy will be faster. The two reactions will continue to occur at the same rate. The prediction cannot be made without additional information. So number 22, if we have larger EA, it will be faster, right? It will be faster. Because we have more energy to achieve to make it happen. Okay, so remember, for number 22, the reaction with different activation energy have the same rate at room temperature. What happened when we raise the temperature? The higher activation energy, the more sensitive the reaction to change in temperature. So at higher temperature, the reaction with larger EA will speed up more. So the answer will be A. Yes. Okay, I just want to double check from the first one, from the number 20. So we know we can use the K. Okay, AE exponential minus EA, and then RT. Remember this one. So when T increase, okay, okay, the fraction of molecule with enough energy to overcome EA increase. Okay, so so it will be faster rate. Activation energy doesn't change. It's property of the reaction itself. Okay, so see, if we increasing the temperature, we will have like faster rate. How about how temperature affect the rate constant K? So the previous one is like, how did the change temperature affect of in the reaction itself? Okay, why this one is double the rate of reaction? Okay, so what's happened to the rate constant, which is K, if we increase the temperature? Okay, so remember, higher temperature, we will have the smaller exponential. Okay, smaller exponential, which is larger K. Because this is minus. Remember, this one is minus. This is always true whether the reaction is endothermic or exothermic. Just remember, if we increase the temperature, we will have the faster rate. We will have we will have the rate constant bigger because the exponential value will be smaller. Okay, smaller exponential. Okay, number 22 still same. The key concept still same. The higher activation energy, okay, it will increase the value of what? No, no. It will increase the sensitive of the reaction. So at higher temperature, if the higher at higher temperature, the reaction with larger EA will speed up more. Okay. So EA will be, so because this one is has a big EA, so it will achieve like the minimum energy to make the reaction happen faster. All right. Number 23, a catalyst increase the rate of reaction by changing the mechanism of reaction. Yes. Increase the activation energy. No. Lowering. Increase the concentration of. No. No. So number 23 might be A. Yeah. Increasing the activation energy of reaction. So kind of like this way. This one. And then this one. Okay. Sometimes like this one. Okay. And then number 24, which statement most accurately describe the behavior of catalyst? Catalyst increase delta G. Nope. Catalyst reduce delta H of reaction. Hence, the temperature needed to produce product. The catalyst reduce the activation energy. Yes, that's true. Number 24 is C. There is no relation between temperature over here. Okay, the catalyst increase the equilibrium constant and final product concentration. Nope. Okay, so only this one, activation energy. Just remember in the like earlier principle, which is adding catalyst no effect on position, only increase the rate. Okay, only increase the rate. Speed up put forward and reverse reaction equally. Reach equilibrium faster but doesn't change where it's ended up. Okay. Number 25. The rate constant for specific reaction at two different temperatures are given in the table. What is the activation energy for the reaction? We have the rate constant and then we have the temperature over here. The question is EA. Okay. So if we are looking at the answer, if we ln K ln A minus EA or RT. Okay, the question is EA itself. So the information is only two. What it is only temperature and rate constant. So we know the ln K1 is 3.010 minus 4 second minus per second, and then we have the ln K2 which is 6.10 minus 2 second, and then we have the temperature. We will use the Kelvin. Okay, so the T1 it will be 400, for the T2 will be 500. Okay, let's take a look at this one first. Okay, so ln K and temperature is kind of like is kind of like inversely proportional. Okay, so the question is about EA. Okay, the question is about EA. let me trying to ln K ln A minus EA RT. Yeah, that's true. So to get the EA RT, it will be ln K ln A. And then we can ignore this. We can ignore this. So minus EA, it will be ln K and then T. Okay? So 1, 1, 1. Okay, EA is same for both. Okay? Um this is me minus this is EA1 and then ln K2 plus T2. What are you looking for? What I'm looking for over here? I don't understand. Oh god. Okay. Okay, so the question is about hmm, it's quite a bit confusing. Okay, it's quite a bit confusing. I think we need to use the Arrhenius equation. Okay, which is ln K2 ln K1 so it should be EA for R minus T1 T2, so this one is 100, right? We know this one is 100. Okay, and then in this case we know that ln 6 times minus 2 and then 3 times minus 4, and then we know EAR is 0.01. Okay, so in this case no way, bro, not like this. If we have 2 point, remember ln K2 K1 and then EA per T up, no, R, right? And then T1 minus T2. Yeah, I just wanted to know like how to get this one. Let me bring from the first one because it will make us more confusing. So we will have like ln K1, right? And then ln A, and then E1 RT1 ln K2 ln A E2 E1 still EA, okay, RT2, okay. And then now we need to what? We need to subtract this data. K2 ln K1, and then we can cancel out this one, right? And then we will have EA per R, okay. This is still minus RT2 plus AA RT1, right? Yep. Now just looking at ln K2 K1, and then we know this one is, we can use AA, and then this one is R, and as you can see this is can T1 because plus, right? And then minus T2. Okay, that's great, that's great. So we can get this bar. So now just put in one by one. Okay, ln 6.10 minus 2, 3.10 minus 4. So let's take a look at this one. Ln 6 times 10 minus 2 divided what? 3 times error terus. Lun. This one have got 5.3. Okay. And then EA or R. You know, R is 8.314. And then this one is 400. 500. Okay. Take one. So it will be 0005 EA. 5,3. So the EA, it will be 88128. This one is still in Joule. Okay. This is minus, right? Minus. So the answer will be plus. Okay, good. So it will be T for the answer. Number 25. T. Yeah, good. Activation energy can be experimentally determined from the slope of the plot of what? EA can be determined by slope of what? See, guys? So over here we see that the equation is ln K, right? And then ln A minus EA RT. So we can plot between ln K, so we can eliminate the option A and B, right? It left just one, ln versus T, or ln versus 1 per T. Okay. The thing that I need to mention here is, okay, we can separate like this way: ln K, okay, minus EA per R, and then per T, and then over here is ln A. So this one is X, another one it will be Y. So this one, the answer will be D. Okay, the slope, this is slope, right? This is slope. So this is A ln K, right? This one is Y. Okay, sorry, this one is X, sorry, this one is Y. Okay, like Y mx plus B. So kind of like this is slope, right? EA per R is slope, X is 1 per T. So the answer will be D. Which energy diagram best matches the proposed mechanism for the exothermic reaction? Remember, exo is release heat, okay? Release heat, which is, it tends toward to product. While endo is tends to heat added. This is in the Oh, sorry, this is in the reactant. Towards in reactant, towards in product. Okay, towards reactant and towards in product. So now remember, we always care for slow reaction. Okay, we always care for the slow reaction. Okay, there are two steps. The energy diagram should have two humps. Okay, the first step is fast and reversible, and then the second one is slow, and then we have and then exothermic final energy. Okay, final energy is lower than starting energy. So exo, which is lower than uh starter starting starting energy. So let's take a look at, we will have two, right? Which one that lower? This one lower, this one lower, so we can eliminate this and this. So, and then again, the first one is fast and then the second one is slow. So if we have the reaction is so fast, so it should be energy that we needed, the energy needed is smaller. So the correct answer 27 should be what? Yes, yes, like I mentioned. Okay, so because this is fast, so the EA should be low. Okay, so this one, right? Because it will achieve like faster. Okay, and then this one is slow because it's higher. Okay, so the answer will be C. Okay, so remember exothermic. Okay, I just wanted to make it more understandable. So the concept of it. So exothermic, which mean the reaction release heat, like I mentioned. Okay, think reactant like the, okay, release energy. So delta H will be minus. Okay, so exothermic is exit of heat. Okay, exo means out. Okay, the heat goes out, and then the products are lower. There is no doubt. Okay, imagine that we are like hiker at the top of mountain. The products are down in warm valley. The hiker goes downhill and drop energy along the way. I don't understand why. How to memorize like exothermic lower final energy? So exo is outside exit. Heat goes out of the system, right? Yes. So energy will be lower. Oh, okay. Energy will be lower. Reactant have more stored energy. Okay. As the reaction happen, the energy is released. Okay. So the product end with less energy. That's why the product are lower on the energy diagram. Oh, okay. I got it. I got it. Okay. So the product. Okay. 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 I got you. Because it releases energy, so it has lower energy than the starting point. Okay, good. Number 28. Which mechanism is or consistent with this rate equation? We know this is the equation. Then which one that consistent? Cl2H2S. We just care about the slow one. So put 1 and 2 probably. Put 1 and 2. 28. Okay, the slow step must include both Cl2 and H2S. Yes. So whichever mechanism has Cl2 and H2S in the slow step is correct. So 1 and 2 is still possible. Oh, however, over here is not H2S. Okay, this one is impossible. Yes, true. So it's only 1. Number 28 is A. Yeah, the last part. The decomposition of hydrogen peroxide in the presence of iodide is believed to occur via this mechanism. In this mechanism, A is catalyst, the activated complex, a reactant in the overall reaction, a product in the overall reaction. Hmm. This looks like only kind of like catalyst, right? Kind of catalyst. If you see, if we combine put together, we can see, see, right? So step one, I is used in the step one. And however, is regenerate in the step two. It appears at the start and end, but not in the overall equation. Okay, this is the definition of catalyst, right? The substance that speed reaction is not consumed. Okay, and is regenerated at the end. So it will be catalyst. Okay. Number 30. What is the relationship between the equilibrium constant of reaction and the rate constant Kf and Kr? Okay. We know in the single step reaction, K is Kf divided by Kr. So the answer will be P. So just remember, key J, key C is product divided by reactant, right? So in the forward rate is K of reactant. Oh, okay. And then in the reverse rate in K product. Okay, good. So in this case, product is was that KR? Huh? Product is so KF forward is reactant, right? KF. Okay. If we are talking about product, it should be KF for forward. So product versus reactant. I don't understand. Like the rate of reaction is rate for the forward is reactant, right? Kf from the reactant. And then for the reverse, Kr from the product. Rates are equal. So Kf and Kr. So Kf now, you know, the Kf reactant. Oh, okay. Kf reactant and then Kr product. So product per reactant is Kf per Kr. Oh, okay, okay, okay. So just quick thing, quick clarification. Kf is what? Because forward, so rate of forward is Kf of reactant, right? Yes. And then this is Rf, okay? For rate of reverse, it will be Kr of product, right? Yes, it is. So now Kc is product divided by reactant. So now just put in product Kc. We want to put in over here. Just put in first Kr product, Kf reactant. Okay. Now let's move on. Let's move this part. So it will be Kf. Okay. And then it will be Kr. Okay. So product divided by reactant. Yes. It will be Kf per Kr. So the answer will be P. Okay. Good. So now we finish for the kinetic and kinetic reaction. So later on we will discuss about acid base and then about for the chapter 11 we will discuss more detail about equilibrium. Okay, equilibrium, and then equilibrium, and then for chapter 12 we will discuss about acid and base. Hopefully we can finish soon for all of part. Okay, so hopefully. Okay, see ya, bye bye.